Let's get started learning about stereoisomerism. Specifically today, we're going to tackle enantiomers and chirality. In order to do this, I need you to make some models. So get your molecular model kit out. And since you probably won't be working with a partner today, you are both student A and student B. So make these two models, then go ahead and make this set of models. So you'll have 4 different models, and then you'll be ready to start. So pause and do that. So welcome back. We're going to start by reviewing isomerism. So go ahead and get your flowchart out or make a blank flowchart just like this, and make sure that you can still add all of these labels to the flowchart, that you can still define all of these terms and give examples of each type of isomer. So this is what your flowchart might look like. Isomers have the same molecular formula, but they are not the same. So they're different in some way. We have 2 big groups of isomers. Constitutional isomers, or the atoms have different connectivities. So you can see for these examples, these are C5H12 isomers. The first one has all 5 carbons in a line. There's branching in the second 2 isomers. And they'll have different boiling points, melting points, solubilities. They are different, though they have the same molecular formula. All right, so the other big group of isomers, and we're going to be working with these today, are stereoisomers. So stereoisomers have different spatial arrangements of atoms. We learned about conformational isomers, which can be related simply by bond rotation. So we learned about eclipsed and staggered ethane, for example. That's what we have here. These can be related by bond rotation. And then we learned about configurational isomers. And configurational isomers, this is where we are today. So these cannot be related by bond rotation. For example, we have cis and trans 2-butene here. If you rotate cis 2-butene to make trans 2-butane, that requires breaking the pi bond. So those are called configurational isomers. They cannot be related by bond rotation. So we're going to zoom in on this area of our flowchart today. All right, so now that we reviewed isomerism, let's take a moment and identify the relationships between these pairs of molecules. So pause and do that. I will look at our first set here. We have C6H14 and C6H14. So they have the same molecular formula, but they're clearly not the same. They differ in how the atoms are connected, how they're bonded to each other. So these are constitutional isomers. If you're ever in doubt, you can always name the molecules, and if they have different names, they're different. So this one has 6 carbons, so it's hexane. Here we have a 4-carbon longest linear chain. So it's a butane. You have 2 1-carbon groups off of carbon 2. So it's going to be 2,2-dimethyl, methyl for 1 carbon, butane. All right, second set of examples here. So we can do our name game. We can also get our models out, or we can just think on paper. If we take this and we just pancake flip it, so grab it and flip it over. Call this a pancake flip. What you're going to get is the same exact molecule. So they are the same. All we had to do was pick this molecule up and flip it over, and they are the same. Now, if that's hard to see, and you should try with your model, you could have named them both. So if we name them, this would be 2-methylpentane. And the molecule on the right, in this orientation, we would number from right to left, and that would also get us 2-methylpentane. Same name, same compound. So these two are the same. Excellent. Let's move to another example. So let's take a look at these 2 pairs of molecules, and we're going to start over here with the trans-2-butene and the cis-2-butene. So let's get our models out. And I want to really hammer home this fact that you cannot interconvert these by bond rotation. So they must be configurational stereoisomers. All right, trans-2-butene, cis-2-butene. If we want to interconvert them, we're going to have to, so I'm going to take my model, cis model, and I'm going to have to I can't, right? I can't make it look like the trans. So I would have to pull it apart. Okay, rearrange. Now I have trans. So I had to break the bonds to interconvert these two. So now I've made the same thing. So these are configurational isomers. And I've redrawn here for you the diagram that we've drawn previously, showing how if you try to rotate between the trans and cis isomers, you break the pi bond. So the pi bond is broken here. The two p orbitals are perpendicular to one another and can no longer overlap. All right, awesome. Let's stay on target for today, though. So for today, I definitely want to focus in on these two molecules. So let's get our model kits out and see whether or not these two are the same or if there's some type of isomer. Now, we can definitely see that the atoms are connected in the same way. So these would both be a 2-butanol, where that alcohol functional group is on that second carbon. But it does look like they vary in their orientation in space. So we have the hydroxyl pointed out towards us in the first model, and the hydrogen on that carbon is back. Whereas in the second molecule, the hydroxyl is back into the page, and the hydrogen is pointed out at us. So let's get our model kits out, and let's see what we can see here. All right, here's the molecule on the left, where you see there's carbon 1, carbon 2, carbon 3, carbon 4. The hydroxyl is coming out of the page, so towards you, and that hydrogen is coming into the page towards me. So here's the molecule on the left, and then on the right, I'm going to get this one out. So the molecule on the right, you have the hydroxyl in the paper towards me, and the hydrogen out towards you. So molecule on the left, molecule on the right, and now we want to see if they're the same. So what you can do to see if they're the same is try to superimpose them. So try to overlay them. And when you try to overlay them, what you can see, and I'll try to help you get a good view here, is that I have my carbon chains aligned. So I have my carbon chains, they're lined up, so they're overlaid with one another. But the problem here is that the hydroxyl for one molecule is overlaying with the hydrogen of the other, and the same for the other one. So here's the hydroxyl of this one molecule, it's overlaid with the hydrogen of the other. So they're not perfectly overlapping with one another. They're not superimposable. So these are not the same. They're not the same thing. So the molecule where the hydroxyl is coming out at you, this one, it's not the same. In fact, the only way that I can interconvert these two would be to actually break these bonds. So break those bonds, and then take the hydroxyl and put it towards me. Take the hydrogen and put it going back. So I'd have to break the bonds, break and reconnect to do that. And so if I have to break the bonds to interconvert, then these two are some sort of configurational isomer. Okay, so we have two sets of configurational stereoisomers here. So let's think about our chart. Aha, here it is. And we'll zoom in a little bit. So we're at configurational stereoisomers. So the bonds must be broken to interconvert the two different molecules. Now we're going to have two types of configurational isomers. And they're represented by the two examples on the previous slide. So I'm going to go ahead and just define those for you. So those two examples, they represent two types of configurational isomers. One type is called enantiomers, and the other type is called diastereomers. Okay, so your example of enantiomers, those are those butanols that we looked at. And an example of diastereomers will be your cis and trans butene. So we're going to go ahead now and we're going to think about the definitions of enantiomers and diastereomers. Now these two molecules, they look really similar, and in fact these are mirror images of one another. Okay, what does that mean? Well, I'm going to show you with my model kit, and then we're going to talk about it more on paper. Here are the two butanols that we've been looking at, and I have them aligned now so that you can see the mirror plane between them. So let me orient you, and I'm sorry, I'm trying not to move my iPad too much. So this one is the one on the left side of the slide where the hydroxyl is coming out at you, and I've just rotated it. And then the molecule on the right is the one with the hydroxyl going into the page. And now when I have them rotated like this, you can see that there's a mirror plane in between them. So this one is mirroring this one. If the mirror was right here, you can see the hydrogens are pointing towards each other. The hydroxyls are mirrored, pointing out. Okay, there's the mirror plane. Now I'm going to draw this on paper for you in a second. And when I draw it on paper, the way I'm going to do it is I'm going to keep them in the orientations that we have drawn on the slide. And then I'm going to make them mirror each other like this. Okay, oops, sorry. Make them mirror each other like this. So you're going to see that the carbon chains are mirroring each other. So I'm going to show you this on paper in just a second. So I'm going to show you now on paper what I was just trying to show you with the models, which is that these two molecules are mirror images of one another. So we'll do it on this slide here. So what I had done with my model kit was I took this molecule on the right and I essentially flipped it over in space. So imagine picking it up and flipping it over. I'm going to number the carbons so you can see what I'm doing. I flipped it over in space so that it ends up looking like this. Okay, so you can go back and you can look at what I just showed you with the models, and that is what it looked like. And then here was the mirror plane in between the two models. Okay, so there was the mirror plane between them. So these were mirror images of one another, but they were non-superimposable, meaning they weren't the same. So remember when I tried to line up the carbon chains, the hydroxyls and the hydrogens were pointing in opposite directions. I'll show you that one more time. They're mirror images of one another, but they are non-superimposable. And this is the definition of enantiomers. Non-superimposable mirror image isomers. Hydroxyl coming out, hydroxyl going in, picked it up, I flipped it over, so that's what I was just showing you on paper, and then now they're mirror images of one another. Okay, the mirror plane is right here. Now I'm going to try to line up the carbon chains to see if they're the same thing, right? Because if we can line them up, we can superimpose them, then they must be the same. But when I try to do that, and it's super awkward to hold my iPad and try to do this at the same time, so you should try yourself as well with your models. I cannot superimpose them, right? The hydrogen, great shot of my wrinkly hand. The hydrogen is superimposed with the hydroxyl group, and same on this one. The carbons are all lined up pretty much, but we don't have the hydroxyl and the hydrogen lined up. They're non-superimposable mirror images, aka enantiomers. Okay, so enantiomers are going to be non-superimposable mirror images. Means that they're not the same. You can't line them up. That's what non-superimposable means. And then diastereomers, these are just configurational isomers that are not enantiomers. And so the one example that we've seen so far is cis versus trans. So for a bit, we're going to zoom in here on enantiomers and think about what this means. Okay, here's what I'd like for you to do, and I'll demonstrate in a moment. I think it's hard to think about this mirror image isomer thing, so I want you to hold your palms up so that they're facing. Your hands are mirror images of one another, and then try to superimpose your hands. Can you do it? Let's watch me do that in my pajamas. So we're going to put my hands up to one another. They are mirroring each other, right? And the mirror plane is right in between my two hands, okay? And now I'm going to try to superimpose them. When I do that, my thumbs are pointing opposite directions, so they're not superimposed. If I try to line up my thumbs, then the top of my hand is aligned with the bottom of my other hand, so they're not superimposed. This is really similar to how the hydroxyl was pointed one way and the hydrogen was pointed the other way. This is like your thumb being lined up with your pinky. So they're non-superimposable mirror image isomers. Those the two butanols we looked at, and your hands, and that's called enantiomers. So we saw with our hands that they are mirror images. The mirror plane was in between them, and no, we could not superimpose them. So because of that, our hands have this property called chirality. All right, so we're going to take a deep breath, one step at a time. So some objects have a property called chirality. A chiral object is non-superimposable with its mirror image. This is like your hands or the two butanols that we looked at. Okay. Now, not all objects have this property. So we also have achiral objects. Achiral objects, they are not chiral, they lack chirality, and they are superimposable with their mirror images. So achiral, they lack chirality. They do not have what's called an enantiomer. Right? So our hands are chiral. The left and the right hand are enantiomers of one another. The two butanols here, they are chiral, and their relationship is that they are enantiomers of one another. This property of chirality is often called handedness, and now I think you know why, because your hands are chiral. Now, some objects have this property and others do not. So you have these two sets of molecules that are mirror images of one another. So you have two tasks. First, you need to convince yourselves that these molecules are indeed mirror images. So if you recall with this set, we actually picked this one up and we turned it around in space. Okay, so now we turned it around in space. When we did that, that hydroxyl now is pointed towards us. And we saw, yeah, there's a mirror plane here. These two molecules are reflecting each other. So now you need to do the same thing with these two molecules. And if you need to, go review, rewind, and look at where I did it for the two butanols. All right, so now you need to try for these are isopropanol. You need to try now and determine whether or not these molecules are chiral or achiral. So on the left, I have propanol where the hydroxyl is coming out at us. And on the right, I have propanol where the hydroxyl is back into the page, going away from us. Now to make them look like mirror images, I'm going to pick this one up and flip it over. And then now you can see there is a mirror plane in between them. Okay, so where the methyl groups are reflecting each other, the hydroxyl groups are reflecting each other, so are the hydrogens in the back. Okay, there's a mirror plane right here in between them. Now I'm going to see if I can superimpose them and hold the iPad all at the same time. So I'm going to pick this up and I'm going to put it on top. And it's super awkward, so let's try over here. I'm going to pick it up and put it on top, and oh, voila, look. Everything is aligned. See, everything is aligned. I need to rotate this hydrogen over here for the hydroxyl, but I can easily do that. Sort of. Okay, everything is aligned. So these are superimposable. And what that means is that since the 2-propanol was superimposable with its mirror image, 2-propanol is achiral. It does not have the property of chirality. And these are not enantiomers. They are the same. So we've examined 2 mirror image isomers that were non-superimposable, so were enantiomers, and 2 mirror image isomers that were superimposable. So they are not enantiomers. In fact, they're just the same thing. These are the same thing. These 2, not the same. They're enantiomers. So you're probably wondering why. Why are some molecules chiral and others achiral? Well, let me tell you why. So it depends on whether or not the molecule has what we call an internal mirror plane. And an internal mirror plane is a plane that splits a molecule into 2 equal halves. So if a molecule has that, then it will be achiral. If a molecule does not have that, then it will be chiral. So let's take a look at that for these 2 molecules. And let's actually do it for 2-propanol first, because it's achiral. And so what that tells me is that it has an internal mirror plane of symmetry. So we're going to see if we can find it. So I'm going to take 2-propanol and I'm going to rotate it in space. And I'm going to rotate it in space so that one methyl group is going into the board and another is coming out. And then the hydroxyl and the hydrogen, they're going to be in the plane of the page. And so when I have done that, once I've done that, I have revealed the internal mirror plane of symmetry, which is just the plane of the page. So this is the internal mirror plane of symmetry for 2-propanol. And so what do I mean by that internal mirror plane of symmetry? Well, the methyl group in the back reflects the methyl in the front. The hydroxyl and the hydrogen, they're sort of cut in half, so half of each reflects the other half. All right, so here's the internal mirror plane. The methyl in the back reflects the methyl in the front, and then like I was saying, half of the hydroxyl reflects the other half because the mirror plane splits it into here, so it's splitting it into. And then half of the hydrogen reflects the other half because it would also be split into by the mirror plane. So the mirror plane is splitting the molecule in half right here. Now let's imagine doing the same thing with the 2-butanol, which is chiral, meaning that it should not have a mirror plane. So it should have no internal mirror plane of symmetry. So we're going to imagine rotating that. And the reason that I'm rotating it is so that the alkyl groups might reflect each other in the plane, right? Just like for 2-propanol, the methyl groups reflected each other. That's what I'm looking to see happen here. All right, so I rotate it, and then I check to see, all right, is the plane of the paper a mirror plane? And no, it is not a mirror plane. So the plane of the paper is not a mirror plane of symmetry. And you can hopefully see why that is. It's not a mirror plane of symmetry because you have methyl in the back trying to reflect ethyl coming out at us. So this is not a mirror plane of symmetry, and therefore 2-butanol is chiral. It will not be superimposable with its mirror image. In other words, it has an enantiomer. Now we're going to rotate. So there we go. And I want to see, is this a mirror plane through the middle of the molecule here? And it is not, because I have methyl in the back. So if this were a mirror plane that splits the molecule in half, just like it did for the 2-propanol, these two groups would have to mirror each other, and they don't. I have methyl here and ethyl here. So there is no mirror plane of symmetry, right? There's nowhere where I can say, okay, this splits the molecule into 2 equal halves. No, because I have a methyl on this side and an ethyl on this side. All right, so we've uncovered the mystery. 2-butanol does not have an internal mirror plane of symmetry, so it is chiral and does have an enantiomer. Its mirror image is its enantiomer. It would be non-superimposable with it. But 2-propanol, it's achiral because it does have an internal mirror plane of symmetry that splits it into 2 halves. So if we drew its mirror image, they're actually going to be exactly the same. You can superimpose them. It's achiral. It does not have an enantiomer, whereas the 2-butanol does. Now, you're probably wondering, oh my goodness, is there an easier way to do this than looking for these internal mirror planes of symmetry? So yes, there is, and what you're going to be looking for is I want you to look for, here's your eyeball, a stereogenic center. So a stereogenic center. This is going to help us. This is much easier to see than these mirror planes. So a stereogenic center is going to be for us a carbon with 4 different groups on it. So a carbon with 4 different groups. So if you look at 2-butanol, you can see it has a stereogenic center. The carbon with a star, it is a stereogenic center. It has hydroxyl, it has hydrogen, it has methyl, and it has ethyl. 4 different groups. And because of that, it didn't have the mirror plane. Meanwhile, if you look at that same carbon on 2-propanol, it is not a stereogenic center. It has hydroxyl, hydrogen, and then 2 methyls. Those are the same. So it only has 3 different groups. And because the 2 methyls were the same, it did have a mirror plane of symmetry. So it'll be easier for us to look for the stereogenic center than it will be probably to look for these mirror planes of symmetry. So let's go ahead and practice now. So I want to ask you about these 3 molecules. Are they chiral or achiral? So again, chiral will mean that it's non-superimposable with its mirror image. In other words, it has an enantiomer. The enantiomer is the mirror image, right? And they will not be the same. I know they're not the same because they're not superimposable, like your hands. Or is the molecule achiral? In other words, it is superimposable or the exact same as its mirror image. So it does not have an enantiomer. Okay, so why don't you pause and try? So I've drawn the mirror images of these 3 molecules for which we want to know, are they chiral or achiral? And the question is, are the 2 mirror images superimposable, which would mean that this would be achiral, or are they non-superimposable, which would mean this would be chiral, and these 2 would be different? That's the question. And so to answer that question, we can do this a couple of ways. Remember, if the molecule itself has an internal mirror plane of symmetry, it'll be achiral. If it doesn't, it'll be chiral. Okay? Now, it can be hard to find these internal mirror planes of symmetry. So I told you that you could look for a stereogenic center, which is a carbon that has 4 or more different groups on it. So these carbons that I've starred here, those will be stereogenic centers. You can see it has 4 different groups on it. So in fact, because there's a stereogenic center there, the starred carbon, this will be chiral, and these will not be the same. They will represent enantiomers. All right, so here are those two molecules. I may have made models of them. I've had to improvise. But here we go. So there's the carbon that has the 4 different groups on it, and I've made its mirror image. And now I'm going to take them and I'm going to try to superimpose them. And when I do that, you can see I've superimposed successfully the carbons and the green atoms and the red atoms, but the white is aligned with purple and the purple is aligned with white. So they are non-superimposable. So these mirror images, they are in fact enantiomers of one another. So you are welcome to repeat this exercise with your models for the remaining 2 compounds. I'm gonna look for the stereogenic centers. So here's a stereogenic center. There's 4 different groups on that carbon. There's hydroxyl, hydrogen, methyl, and vinyl, the double bond. 4 different groups. That is a stereogenic center. Now I did draw the mirror image. This would be the enantiomer. So these two have a relationship. They're enantiomers. Because of that stereogenic center, these molecules are chiral and they will have an enantiomer. They will be non-superimposable with their mirror image. And then finally, if we take a look at this last example, it can be tempting to say, hey, this carbon, you've shown stereochemistry, you've shown in and out. Is that a stereogenic center? Well, no, it is not. There are these 2 different groups, methyl and hydroxyl, but look, this part of the ring, it's exactly the same as this part. In fact, there's an internal mirror plane of symmetry here. And because there's that internal mirror plane of symmetry, and that carbon is not a stereogenic center, then this molecule is achiral. It is not enantiomers with its mirror image. They are exactly the same. They're the same molecule. It does not have an enantiomer. So can you draw an enantiomer for a given molecule? Sure you can. Determine if that molecule is chiral, and if it is, draw its mirror image. Put your little mirror plane and draw its mirror image. It's fun. It's art class. Okay, let's summarize. How can I tell if a molecule is chiral? Well, what will always be true is what I've written here about the mirror planes. If it has an internal mirror plane of symmetry, the molecule is achiral. It does not have an enantiomer. It is the exact same as its mirror image isomer. If the answer is no, there is no internal plane of symmetry, then it does have an enantiomer, and that enantiomer will be its mirror image. Now, that can be really hard to see those mirror planes of symmetry, right? So there's another way that we can think about this. We can look for that stereogenic center. So does the molecule have a stereogenic center? If the answer is no, it does not. So that was your carbon with 4 different groups. If it doesn't have a stereogenic center, then that means the molecule is going to be achiral. It will have that internal mirror plane. Now, if the answer is yes, it does have a stereogenic center, we do have to think about one more question. If there's only one stereogenic center, then the molecule is chiral. But if there's more than one stereogenic center, the molecule might be chiral. We just need to double check for a mirror plane, right? Double check for this always symmetry element here. Before we end our video, I just want to come back to the molecule that we started with. So this is an isomer of 2-butanol, or if you use the newer IUPAC naming rules, that 2 goes in the name. Not important right now. Now, we know that this is a chiral molecule because we see the stereogenic center. So can we draw its enantiomer? We could, yeah, for sure. We can draw a mirror plane, and I'm going to mirror out. Okay. So this is its mirror image, and this would be its enantiomer. Now, you might not want to draw a mirror plane and mirror the molecule. So there's another way that you can draw its enantiomer. So what I'm going to imagine doing is taking that stereogenic center, I'm going to break those two bonds, and I'm going to swap the groups. I'm only going to do it with two of the bonds, right? So I broke the OH bond, let's put an H. I broke the H bond, I'm going to swap, put the OH. So I've swapped these two groups, and two groups only on the stereogenic center. So look, the carbon chain is exactly the same, right? So now this is another way of drawing the enantiomer of that 2-butanol that I started out with, right? Of course, these two are the same. We started out by taking this and flipping it over in space. When you do that, when you pancake flip it, you'll just get this one. Okay, they're the same. Convince yourself of that. So here we have two ways of drawing an enantiomer. Okay, we can just brute force draw the mirror image. Right? I will ask you to draw the enantiomer of this. Just brute force draw the mirror image. Or you can do what I call, or is called, switching the configuration of the stereo center. And I come back to what that term configurational isomer means. It means that you had to break bonds to interconvert two things. So I'm literally doing that, right? I'm breaking these two bonds, and then I'm swapping the hydroxyl for the OH. So that's how I drew this configurational isomer. I just switched two of the groups on the stereo center. Now, what we were planning to end with was actually learning how to name these molecules, because so far, we would call both of these 2-butanol. And they can't both be 2-butanol because they're not the same. So we're going to have to describe what's called the configuration of the stereo center, and that's going to be using this RS system, and I'm going to do that in a separate video. Let's think about, though, what we have learned, though. We've learned to identify configurational stereoisomers, including enantiomers and diastereomers. And we'll go back to that chart in just a second. We're going to learn R and S in a later video. And you're able to identify mirror planes of symmetry. So those are those internal ones in organic molecules. And you're also able to identify stereogenic centers. Okay. Let's just end with that flow chart. Make sure we understand enantiomers and diastereomers. So there's going to be two types of configurational stereoisomers where bonds must be broken to interconvert. The type we've talked about today is enantiomers, where we have two non-superimposable mirror image isomers. And then we have diastereomers, which are everything else. Time to practice.